Hi, my name is Soumya Basu, and I'm here today to talk to you about Trustless IoT, a logic-driven architecture for IoT hubs. This is joint work with Emin at Cornell University. If we look at IoT, there are projected to be 5.8 billion devices by the end of 2020. This is a 20% year-over-year increase from 2019, which is a 20% year-over-year increase from 2018. IoT devices are deployed across many major sectors of the economy, ranging from energy to cars and car manufacturing to government. So IoT is pretty big, and we see that it's standardizing around one architecture using centralized hubs. And what this means is essentially you have a small number of hubs that effectively control all 5.8 billion IoT devices. We believe that hubs are here to stay for three reasons. The first is hubs make it simple to administer and control your large-scale distributed complicated IoT system. There's one place where you have to go in order to enact any changes or reason about what your system is doing. Second is hubs are pretty complicated pieces of software and hardware to write and manufacture. So hub vendors will benefit from economies of scale. So you won't have too many different vendors to choose from. And finally, if we look at devices themselves, they have limited communication modalities. So you can't maintain connections between devices, say such as in a peer-to-peer setting, which requires devices to maintain many connections. So you really have to kind of rely on one or a few centralized points for basic communication. So just as a side note, when I talk about devices have two parts to them. They have actuators that act on the environment. So think about your air conditioning unit, which cools the ambient temperature of the room. Or you have sensors which read values from the environment, such as your thermostat, which reads the ambient temperature of the room. So what about security? The state of IoT security is quite poor. And as you may have heard, the S in IoT stands for security. When I talk about IoT security, there's really two parts to this. The first part is device security, which is how do I make sure that my smart thermostat or smart refrigerator doesn't get hacked and compromised and do the wrong thing. And the second is hub security, which is how do I make sure that my Alexa doesn't get hacked so that it tells my refrigerator the wrong thing and spoils all my food, for example. And we've seen many examples of unauthorized access to devices, such as the Jeep that was hacked and driven off a ditch remotely, a vulnerability in cardiac devices that would allow a malicious user or a malicious attacker to decrease its battery power and decrease its lifetime. And we've heard the classic story of a hacker who hijacked a baby monitor and talked to some family's poor baby. So why is security poor, though? And the root cause is implicit full trust is placed in the hub. And this is problematic because hubs are in the TCB of every device. And what this means is if a hub is compromised, then every device has a point of entry in order to access some of its features. Hubs are also always on and interconnected, and internet connected, which means that attackers can attack hubs from anywhere and have ample opportunity to do so. And finally, hubs are all powerful. They can commandeer any action on any actuator. So if you have access to a hub, you can get the IoT system to do anything you want. And now if we start piecing together the critical role hubs play in IoT systems and the wide range of industries that IoT systems are party to, a hub compromise can have national security implications. So for example, instead of ruining the temperature of your fridge and ruining the food inside, you can easily imagine a case where a national food stockpile gets ruined or a large warehouse or something. And then now that affects the food supply of the entire country. So what do we do to fix this? We present the OrbanHub proposal, which is a modified IoT architecture where hubs can't misbehave. And what we do is we make sure that a Byzantine or compromised hub is constrained in its actions. And there are two guarantees we provide even when a hub is compromised. The first is safety, which is that no command is executed by any device unless it's authorized by some user's policy. So the only way the air conditioning unit will turn on is if if there exists a user policy that will tell the air conditioner to turn on. And the second guarantee we provide is a liveness guarantee, which is that all commands that should be executed will eventually execute. So if, for example, the user's policy says the air conditioner should turn on at 5 p.m., then at 5 p.m. the air conditioner will turn on. And a design goal for OrbanHub is to make sure that it's lightweight and incrementally deployable so that it can be implemented on modern IoT chips. So, to guarantee safety, we use this technique called proof-carrying statements. And what proof-carrying statements are is when a hub sends an action to an actuator, such as the hub telling the air conditioner to turn on, it must accompany it with a proof that this action was authorized by some end user policy. So essentially all actions have to have justification attached to it. Now, sensors will upload cryptographically signed statements that will serve as inputs to these proofs so that these proof-carrying statements can then be generated. And the hubs are the ones who are tasked to generate these proof-carrying statements. And what this essentially does is make sure that the hubs can't engage in any actions that are unjustified and not backed by an end user policy. So let's look at a sample proof because that was kind of high level. So if we look at a concrete user policy that says, if the door is open, turn the porch lights on. So we'll let rho be the user policy, phi be the statement door is open, and tau be the statement lights turn on. So rho is the policy that phi implies tau. So if we look at the door sensor will at some point notice, hey, the door is open, and it will send that signed statement out, and it will send phi out. And the hub will then construct this user inference, pi. And the user inference starts as follows. It says, the door sensor says phi, and because the user trusts the door sensor to say things about the door, the user will also say phi. So the user will agree with the door sensor and say that the door is open. Now the user is saying that the door is open, and it has the user policy rho, which says that if the door is open, the lights turn on. Given rho and phi, we can make the inference that tau must also be true. Now, we know that tau is true, and once this user inference is sent to the light actuator will then check this proof and then will turn on because of the user inference. If we look at the control flow of this system, it's pretty simple. You have the door lock, you have the lights, you have the hub. The hub is storing the policy rho, which is that phi implies tau. At some point, when the door is open, the door lock will detect it and will send phi to the hub. The hub will then construct the proof pi like we talked about on the previous slide, send pi to the lights, and the lights will then turn on. To guarantee liveness, we use a different technique. We log all statements using a hash chain. And what hash chains do is they constrain the hub to deleting just the tail of the log. Because if any middle entry of the log is missing, a device will be able to tell because of the properties of hash chains. So this still allows the device, the hub, to send stale updates. To prevent that from happening, we require all devices to send periodic updates. So every so often, we must hear something from a device. So the door sensor every, say, 10 minutes must say that the door is open or the door is closed. It doesn't matter which one. And what periodic updates do is they prevent the hub from withholding the update forever, because because the hub because the hub cannot delete any middle entry, and we know that the last entry of the log um, must be as long as the update, it can only be as old as the update period. So if a device is quiet for too long, we can safely generate some failure alert. And then at that point, depending on what failed, whether it was the hub being malicious or whether it was a device that failed, there's a range of potential fallback mechanisms. So we present a new way forward. IoT is becoming more and more ubiquitous, and attacks are becoming more lucrative as a result. Imagine if you're just attacking hobbyists versus attacking a country's government or a country's food supply. Security is a first-class concern in the latter case. It becomes critically important to secure your IoT systems. To that end, we present OrbanHub, a new trustless IoT model that works with the existing architecture and maintains hubs, the hub architecture, and it has limited overhead on devices as they're only responsible for checking proofs. Thank you very much for listening to my talk. I'm happy to take your questions now, and if you have more, I'm happy to take more questions offline. Feel free to contact me at soumya@cs.cornell.edu. Thank you.